Hello everyone, I'm Riley Miladi. I'm a machine learning research engineer at Embark, and I'm going to be talking about automated physically based animation through reinforcement learning today. I'm going to start by talking about what is physically based animation and why I think we should use it. And I'm going to then show you where we are at Embark and talk a little bit about how do we make these physically based animations, and then go a little bit into details of how we make them by using techniques like curriculum learning and multitask learning. And lastly, I'll talk a little bit about some of the challenges we've had. Before I start, I should mention that this slide and the next slide is from my presentation from my colleague Tom Solberry at NDC. I highly recommend that you watch it. And before I start talking about physically based animation, I think it might be useful to talk a little bit about physically based rendering. And before physically based rendering, shading and computer graphics and rendering was mostly based on what looked good rather than what was correct. But physically based rendering turned that on its head a little bit, and we started making games and animations and films with those physically based constraints, and then which achieved more realistic results. And we did that by studying light and energy transmission. For physically based animation, that's the same idea, but of course for animation. In this world view, we treat the creatures as robots in a physically simulated world. And in this world, like I don't walk by moving my limbs. I walk by pushing a force from my leg to the ground, angling myself, and the normal force pushes me forward. So you might be asking, why should we use physically based animation? And the main motivation for us was that traditional animation is quite difficult and it's quite time consuming and it needs a lot of expertise to make them. And we really wanted to allow anyone to bring the creatures they've made to life. And that's that we needed to automate this process somehow. And that brought us to physically based animation. And beside automation, I think we can get a lot of other benefits from it as well, like realism and groundedness. So we as humans are really good at telling when things around us move in a physically impossible way, and that just looks off to us. And this is a problem that you see a lot in traditional animation, since again, that we go based on what looks good. And like to give you an example of this, I'm going to show an exaggerated example from some of the work of animation that my girlfriend did in the first year of uni. And this is again an exaggerated example of this. And don't worry, she's not an animator, she's an environment artist now. And as you can see, even though the skills are here, but something looks off about this, and that's because the physics is not correct. And like this becomes immediately very noticeable for us. And of course, this gets better over time. Like experienced animator, of course, is not like this. It's a lot better, but this is just an exaggerated example to highlight that. And this is a problem that you don't have in physically based animation, because the only thing you're concerned about is physics and the physics being correct. And also some of the other, I think, interesting aspects of physical animation is like the interaction that it can add. I think that can add a lot of immersiveness and emergence to the game, like Wasabi being hit by the cube here. And Wasabi wasn't scripted to react to this, as we haven't done anything for this interaction. This is just something that you get for free. And to get a little bit of a better sense of our motivation for doing this, I think it would be useful to show some of the results. And you might have seen Wasabi before in a blog post that we have put out. And to clarify things, our animation efforts at Embark are divided between two groups. One is Wasabi, and with Wasabi, we try to find out what is the maximum quality of animation we can get by a lot of expert fine-tuning. And for now, focus is on large robots. And again, I should mention, there was no animating done here, and there was no animation references used. Wasabi learns to do all of these motions and gates on its own. And the other project that we're working on is Moro, and that's the project I'm working on. With Moro, the goal is a little bit different. We try to find what's the maximum diversity that we can achieve. And by diversity, I mean the diversity of the creatures that we train, the diversity of the type of environments that they act in, and the type of task that they do. And our goal is to be able to animate any arbitrary creature with as little user input as possible from users that might not be experts either. And of course, for this means that they have to be, creatures have to be physically possible for them to make those movements. And with that, hopefully, when you set up these parameters correctly, the weights of the body and the shape, you kind of get emergent behaviors like the real animal. Like the seal here has never seen an actual seal, but because of this constraint, it kind of walks like a seal. And that's kind of the goal. And this system is also extendable to flying creatures. Like here, we are just estimating the aerodynamics of flying of a bird and adding that to our physics simulation. And it works for flying creatures now as well. And the goal of these creatures here is to reach the green box here. That's how they learn to walk. And with Burgerman here, that was notoriously difficult to train, and as two-legged creatures are very hard to balance. And we're really proud that we got this result, even though it looks a little drunk. And I should mention that the two projects share a lot of the same techniques and resources. But for now, our goals is a little bit different, but we're hoping in the future to have the diversity that we have here with the quality of Wasabi with very little user input, if any. And the way we do this is we start by making the creatures in the first place, and we set the creatures up by defining their joints and the properties of them, like how it can move it, the damping of it, and we set the weights of the different body parts, and then we set the strength for the motors or muscles. And again, I should mention that these, like robots, like actual robots, like these parameters need to be set in a correct way. Like, for example, the same way that you can't have an extremely heavy robot with very weak motors. The same thing wouldn't work here as well. Like it needs to be physically reasonable for it to be able to learn these movements. And so now that we have this virtual robot, so how does it learn to walk? And the answer to that is reinforcement learning. In short, reinforcement learning is what you might know as conditioning, which is how we teach dogs or other animals how to learn, or even how we teach other humans. And in reinforcement learning, the idea behind it is that we reward or reinforce behaviors that we like. For example, for your dog, if you want to teach them to sit, like you can give them a reward every time they do that, and hopefully over time they can get better and better at it. And we use the same idea here. And in reinforcement learning, you have two parts, the environment and the agent. The environment here is the physical simulation and this terrain, and the goal, that's this green box, and the shape of this terrain. And the agent is the Burgerman here that tries to reach that goal. And at each time step from the environment, we get some observations that describe the state of that environment and the state of Burgerman. And by that, what I mean is it just tells us where is the goal, what type of shape of terrain we are on, what is the friction of the ground maybe, and also some information about the Burgerman itself, like what is the position of and rotation of the different joints, or what is the velocity of the different body parts. And that observations here goes to our actor, or which is a function, or we also call this a policy function. And this functions are anything that gets an input and gives you an output. And the input for this function is the observation, and the output is the actions that Burgerman takes in this environment. And the actions are how much force to be put we apply to different joints with our motors here, kind of like a real robot. And then in return, our environment gives back us a reward that tells us how well we did it for that task. And to give you an example of what a reward might look like, for example, if Burgerman reaches the green box here, we give a positive reward because that we want that. Or if the Burgerman falls, that's a negative reward. That's not a behavior that we want. Or if like Burgerman goes to the green box with the speed we wanted, that's another positive reward. And these actions, rewards, and observations go to our critic, or what we call Q or value function. And that in return updates our policy to make to get better rewards in the future. And I'll talk a little bit more about how does that work. To make things a little bit clear, I mentioned function is anything that takes an input and gives you an output. And in theory, you could use any of these functions, but in practice, we usually end up just using differentiable functions, which are mostly neural networks. And the policy and the critic that I've mentioned before, these are both deep neural networks that we use. And for now, you don't need to know how a neural network works, but just know that you get an input, in this case, the observation, and some mathematical operation happens inside the network based on the parameters of that network that gives you an output. And the output changes depending on what parameters you have inside your network. And the goal here is to find the right parameters that give you the right output. And one of the most common ways that we find these parameters in reinforcement learning is with an umbrella of techniques called actor critic. And at Embark, we specifically use one of these techniques a lot called soft actor critic, or SAC, but for this case, I'll just stick with the basic case of actor critic. And in actor critic, you have an actor, which is our policy here, and a critic, which is our value function here. And the job of this value function here is to estimate the value of each state or each state and action. And by value, I just mean is our estimate of how much reward do we think our policy is going to be able to get in the future. And that's what we call the value of that state or that state and action. And then the job of our policy then becomes to maximize that value. And then we optimize these two different functions jointly. And that's how we learn. And the way we learn the value here is by looking at our past experiences and seeing what rewards did we get in those cases. And in reinforcement learning, generally, most of the research has been done on the RL algorithm side, and environment is an often overlooked part. And that's what we've been spending a lot of our resources on at Embark. And the reason for that is that we wanted our agents to be able to act in all sorts of different environments. And by that, I mean, that might be a different gravity, or it might be a different friction for the ground, or bounciness, or it might be different shapes of terrain. And since you have all these different types of environment in a game, we want to be able to support all of that for our agents as well. And in this particular example, I'm going to just focus on the shape of the terrain here. To be able to achieve this, at first, what we did was we went a bit of a naive route. And at the beginning of each episode, we generated a procedural terrain like you see here. And then Lizzie, our lizard here, would observe it with some raycast from above. And the result of that looks a little bit like the vision grid that you see here. That gives us the height map of this terrain that is around our character. But this turned out to work pretty terribly. And the reason for that is quite intuitive. And to understand it a bit better, this is a little bit like taking a toddler who hasn't learned to walk yet on Mount Everest and asking them to learn to walk there. It's a big ask. And for us to get around that problem, we started looking into curriculum learning. The idea behind curriculum learning is, again, quite intuitive. And the idea is that if you want to learn something complicated, like integrating or walking on Mount Everest, you need to start learning the simplest form of that problem, like addition here, and then start making the complexity more and more over time, like learning multiplication or equations while learning what they are, and then you can learn integrating over time. And to do this, we started looking at this paper by ETH University called Quadrupedal Locomotion over Challenging Terrain, which is for the domain of robotics, but it still applies to our problem. And we extended this a little bit and made it improved for our use cases, but I won't go to the details of that. I'll just explain the base case here. And what our curriculum does is like it has a set of particle filters that define the distribution of the environment parameters based on the score that our agents get in those environments. And what that means is like simply these particles try to estimate the difficulty of each of these environment parameters that define our environment. And by environment parameter here, I mean, again, it could be the friction, it could be the gravity, or in this case is the roughness, frequency, and amplitude of our terrain. And based on that, we get a score, which is this traversability. And the higher that score, the better, the easier that environment is. And as you can see, like as the environment gets more difficult here, also the traversability scores goes lower. And just like biological agents, like our goal of curriculum is to give a level of difficulty that it's challenging enough that we learn something from it, but it's not so difficult that we don't learn anything from it and we don't make any progress. And there is a sweet spot of difficulty, so to say, and our goal is to find that sweet spot, basically. And the way we do that is by, at first we randomly sample the initial terrain parameters, and then we do a random walk, which is just adding random noise to those parameters. And then we let our agents go through that environment and then calculate a score of how well they did in each environment. And based on that, we update the sampling weights of these particles, which we calculate using this. And all you need to know about this is beta here is that sweet spot of difficulty that I was talking about, and alpha is the sensitivity, and S is the score we get. And all this means is the closer our score is to that sweet spot of difficulty, the higher likeliness of that our particles gets resampled. And we keep repeating this process. And in the meantime, we also update our policy or our agent. And what that happens is that our agent gets better over time, and that also changes the definition of like what's difficult in this environment, since our agent's capability has improved. So this kind of makes this sort of feedback loop that the policy and the curriculum evolve together. And what that looks like is that you'll see that it starts with the simplest case of the environment and slowly increase the capability until it reaches the maximum capability of the agent. And in practice, that looks a little bit like this. You start by the simplest case and hopefully it gets a bit more complicated over time. And again, I should mention that two-legged creatures are notoriously hard to train because of the lack of balance. And before curriculum learning, they weren't able to walk on terrains at all. But I think, as you hopefully see, they do pretty well now, I think. This is quite a challenging terrain for a lot of us, I think, as well. But as you can see, it does pretty well here. And after it's trained on these harder terrains, like it will, as you'll see in a second, it will start reaching the maximum capability of the agent. And that looks a bit something like this. And like you'll see this creature fall here, but even though it falls in this really difficult terrain, it still does okay, I think, which is, I think, quite impressive depending on the shape of this creature and the short legs that it has. I think we were surprised by what its maximum physical capability was. And so we initially started by focusing on these terrains and walking, but of course that's not enough. That's not the only thing creatures do in a game. Beside walking and running, they stand in place, they spin, they jump, they might dance, they might do a lot of things that we haven't talked about yet. And for that, we started like working on multitask learning. And the way we do that is we define a reward for each task here, and each one has a different set of rewards than the other one. And we just tell Lizzie which task we want it to perform. One major problem that we had when we were working on this is that defining a reward for some task is quite difficult. For example, it's not that difficult to define jumping, but how do you mathematically define dancing across all creatures? I'm not really sure if that's even possible. And that's why we have been looking into some methods that don't use rewards, like imitation learning and unsupervised reinforcement learning. And I think this is where the interesting next steps could be for this type of methods. So what are some of the challenges we've had along the way? I think the main one would be the resources. This has taken a lot of resources to build, and building these platforms from scratch, it takes a lot of expertise and a lot of time and resources, and we still have a long way to go. And we have transformed this problem from problem of animation to problem of robotics, which is quite a difficult problem to solve. And we are trying to solve robotics for any arbitrary creature, which is even a harder problem to solve. Usually robots in the real world are very optimized and very fine-tuned, and it can be quite difficult to be able to learn that all by its own. And as this is a complicated problem, it needs a complicated solution, which can be a bit hard to debug sometimes. And some of these problems are your typical software engineering bugs. Some are your typical physics bugs that you see in a lot of games, like getting stuck on the ground. But some of them are a bit weirder and more interesting and can be a little bit harder to debug as well. Like you have this polar bear here that walks backward because this heading direction was set wrong, or the spider that just has too much power and it looks a little bit ridiculous. And sometimes everything's set up correctly, but it just doesn't do it the way that you want to do it. Like Lizzie walking like a biped, or this creature walking a little bit like a gorilla, which is a technically correct solution, but just not what we wanted, probably. Thank you so much for listening. If there's any questions, we'll be happy to answer. Ruben asked, what type of animation playback performance do you get on any given trained model? Curious to know how it compares to traditional state machine-based solutions. So surprisingly, the performance is not too bad after they're trained. The training can take a really long time, but once the models are trained, they can be quite small for reinforcement learning, the models. And I'm not sure about the exact performance of that, but on a normal computer, like we've had more than 40, 50 creature at the same time, and it seems to be able to handle it okay. And it's not the model that takes most of the computation. It's generally like the observations that it gets from the environment, like those raycasts that you get for the terrain shape. So there's definitely lots of room for optimization beyond that as well.
If you have questions,
Robin asked, very cool. Have you seen Trace, by the way, an old analysis of how physical objects vary used in product design, but essentially a guide to millions of variations by function and style and material components? No, unfortunately, I haven't seen it. I'll definitely check it out. But yeah, this is definitely something that we see a lot by just different ways of setting these physical parameters, like sometimes just setting the density of this the different body parts, like you see a completely different gait and a complete different behaviors, and that's been really interesting to see. It can be a little bit addictive to watch them almost. Tuan, I'm sorry if I'm pronouncing your name wrong. So it's kind of an adversarial reinforcement learning algorithm. That's very cool. There are parts of it that are adversarial, but not all of it. For example, we do some adversarial training. So for example, like we push them sometimes and we throw boxes at them and like things like winds, and we simulate this type of stuff so to make them more robust. But yeah, this helps to like make them a bit more robust, but I wouldn't say that it's like a necessary part of this. It's more of a robustness thing for our setup. But there are other methods like Gale that their focus is on adversarialness of this, and they look a little bit more like GAN training. James asked, where do you think the limits of this technique lie? I would say the main limit would be maybe stylized animation. Like a lot of the time, what you want is not physically based animation. You want it to have style. You don't want it to be physically accurate. I don't think this makes sense for that type of scenarios, or when you need very, very accurate and very predictable motions. I don't think it's also very good choice for there. So for example, fighting games can a lot of the time need very accurate animations in the way that, and they need to be very predictable for the gameplay to work. It's probably not the best use case for that type of games either.
Riley, could you check the
the
questions in the chat?
If the agents like Burgerman and the Blue Head, it's a large mess with arms and legs attached. As you said, bipeds are notoriously tough to train, but could the models not being automatically correct play a role in this? As humans have spines and hips to help shift our ways to allow us to better walk and move. Yeah, this is a problem. I think there's a few parts to this. Like one is that like the limitations of the physics simulation, like you said, like we have different body parts that like allow us to like to shift our weights, and like it's not always like easy to get this in the physics simulation. The inaccuracies that you can have there can lead to the gate not looking exactly natural. And another thing is like we've never shown human motion to them. So, and their goal is not to replicate human motion. Their goal is to just reach there. And that can sometimes bring this weird gates. Like one of the things that we've tried that helps here is a energy penalty that we essentially ask these agents to be as energy efficient as possible. And that a lot of the times makes this mess of movements and this drunk type of behavior a bit better. But yeah, that's definitely something we look into, and we are looking into other methods as well that we can give them a small reference so they can try to replicate that.
Riley?
Yes.
Yes, we actually have a few questions in the chat. Like we actually send it to the chat directly to you. Could you check that?
Yeah,
there are questions from the audience here.
Great. I was wondering, is it possible to get rid of the jittery toddler-like quality of the box through reinforcement learning as well? Yeah, that's again with the energy efficiency. That's one of the things that helps a lot with the jitteriness of this. And again, the jitteriness part of it is also from our physics simulation. The physics simulation we use wasn't designed for simulating creatures, and we are looking into like articulation is a big factor in this, and like using physics simulation that use articulation helps a lot with that jitteriness, and the energy efficiency is again another way to tackle this. And Christoph asked, is there any API or library that you would recommend for exploring this space? We are actually going to be releasing an open sourcing part of this, and like I'll definitely recommend to have a look at that when you can. But some other libraries to look at, like recently Isaac Gym has been released, and it comes with a lot of interesting examples in this area. So and it's extremely fast since all based on GPU, and it cuts down a lot of the inefficiencies. Like I think that's a really great place to start playing around with this kind of things.
All right. Thanks, Riley. Unfortunately, time is over, and we're going to take the lunch break now. Thanks very much.
Thank you very much.